Okay, so today we go into chapter 15, which revisits the timers. Let's jump right into it. The topics for today are just some basics on timing and frequency. We'll go back through timer 0 real quickly, and we're going to go into wave generation and then capturing waves. The whole point of wave generation, as far as I'm concerned, is to eliminate overhead. So for homework, you had to generate a square wave, a delay of 7.5 microseconds. Now we're going to learn how to do that without any overhead and without interrupts. So just so that we're all on the same page here, the period of a wave is the time between falling edges, or you could say it's the time between rising edges. It's the same time. Okay, that's the period of a wave, usually denoted with tau. And the frequency is 1 over the period, and it's usually measured in hertz. Hertz usually can be called cycles per second. These are the same thing, hertz, cycles per second. So the units on that are always 1 over seconds. Okay, the duty cycle of a waveform is, if we have a fixed period, that doesn't necessarily mean that it's on for the same amount of time that it's off for. We could have it on for substantially less time than we have it on for. And so it's just a ratio of that. You could call it the time off over the period times 100, or the time off over T0 plus T1, which is still the period times 100. It's the duty cycle. And finally, the amplitude of a waveform is just the peak-to-peak voltage. Now, in our case, we're always going 0 to 5 volts because we have a digital system. But those are 3 things talking about any kind of wave. This is a square wave. We could have sine waves, triangle waves, all sorts of good stuff. But period is the time between like points. Duty cycle is the amount of time it spends high over the amount of time it spends low. And amplitude is its peak-to-peak voltage. Okay, everybody's familiar with music, I think, at some level. You've heard music. Music on a keyboard or a piano is made up of notes, usually labeled A through G. And A through G make up an octave. And each of these corresponds to specific frequencies in hertz. The nice integer one is the A key. That's A4 in the 4th octave. And it's 440 cycles per second. So 440 sine waves per second. And if you go up an octave, you see that it doubles up to 880. So it fits twice as many sine waves in the same period of time. And if you go down an octave, it halves the frequency. Now, A is the nice and easy one. It's 220, 440, 880. Okay. In between those, however, it's fractional frequencies. We also have sharps and flats. Okay. But we can generate these with a fair accuracy using the waveform generation unit. Now, this is all of the units inside the ATmega32 and all of the ones inside the 328P. It's very difficult to see because each of these takes up about 1/3 of the page. So let's just look at timer 0 all on its own. You'll notice in the 328P, it's identical. It's the same pieces every time. So here it is, timer 0 in review. All right, timer 0, we have our free running counter, okay, and we've got our 2 compare registers and our 2 comparators. So the free running counter goes to both comparators. And we've seen that flags get set when the 2 things match. Okay, that was the essence of CTC mode. Right? We also have somewhere, okay, not shown here, we have our T overflow flags and all that other good stuff. But we sort of skipped everything to the right of this diagram. Yeah, we know about flags, we know about the comparator and OCR, but all this stuff, this is new. However, there is something that you should have seen before. What is this section in blue? What's that? What is DDRD? What's port D? Data direction register. Yeah, DDRD is the data direction register. It's port IO. It's the port IO stuff. There's your tri-state buffer, okay, to indicate whether or not you're an output. But there's sort of this extra piece. We used to say that the port pin went directly to the tri-state buffer. For these particular pins, D6 and D5, for those particular pins, there's some extra stuff because these have a secondary function. They're output compare pins. We can generate waveforms with no overhead, all done in hardware, okay, on those two pins for these two things. So we can generate a waveform based on OCR-A on pin D6, and we can generate based on OCR-B on D5. So the trick here, and the new piece that we have to cover today, is these two fields, the COM bits, C-O-M. All right. Before we get there, though, let's make sure we understand everything else that's going on in these control registers. First off, clock source bits. We know that we've got pre-scaling or external events or turned off. Okay. For waveform generation, we've used normal mode and CTC mode before. It's those 3 bits highlighted in green there. Today we're going to be dealing with PWM modes, probably just fast PWM modes. Okay, and we'll get into that, why there might be 2 different. I want you to notice that there is this top value that says what you're counting to. So with mode 3, it always counts up to FF and then resets, and counts up to FF and resets. Unlike CTC mode, which if this is FF and this is 0 here, might only count up to this value and reset because that's your OCR value. So it's going to go faster because it doesn't have to count as high. So counting to FF is different from counting to OCR. So mode 7 kind of combines mode 3 and mode 4. Mode 3 is PWM mode, where it always counts to FF, which is kind of like normal mode. Mode 7 is also a PWM mode, but it counts up to OCR. So we'll see how that gets into it in a second. All right, so clock source bits, we've done, yeah, pre-scaler. These are from previous slides. We've got CTC mode and we've got normal mode taken care of. We've seen those before. Today we're going to be mostly talking about fast PWM mode. I don't think I need to do this again. Normal mode, we know what happens. Counts up. The overflow flag is going to get set. Yep, animation. This should be a review. If anybody needs me to stop and go over this again, now's the time to tell me. Otherwise, I'm going to fly through this part. Going once. Going all right. I see a bunch of shaking heads. CTC mode, very similar, except it changes where you count up to. And instead of the overflow flag, it's the output compare flag. But otherwise, it still counts up over time. Great. And when it hits that OCR value and resets, that's when we have our flag. Fine. Here's the waveform generator in a nutshell. We know that basic I/O says, all right, if it's a 1, the tri-state buffer is enabled, so we go right through, and whatever appears in this flip-flop shows up as 0 or 5 volts on the output. Well, for 2 pins concerning timer 0, that's not quite correct. In between the port register and the tri-state buffer, we add in a little bit more circuitry. We add in this multiplexer. Most of the time, when we're not doing waveform generation, it goes straight through, okay? It acts like the mux isn't there. But, notice here, these are these COM bits, compare output mode. If the compare output mode is anything other than turned off, we no longer get our input for this pin from this register. Now we get it from the waveform generator. So instead, comes out of here and goes through the mux to this driver. So the takeaway from this first diagram is for waveform generation, you must set the DDR register equal to 1. The DDR bit must be set to 1. If it's set to 0, yeah, you'll be generating a waveform. It'll be going off, doing its thing, but the tri-state buffer will be disabled.
Which DDR is it?
Specifically, it depends on what channel you're doing. All right, so we have 3 timers. Each of those has 2 channels of output. In this case, it says that it's pin B3 for OC0. That's a 328p specific one. All right, if you go back to the diagram that I put together for, oh my goodness, that's quite a few diagrams. I want to go here. If you go here, it's tough to see, but it's D6, D5 for timer 0, B1, B2 for timer 1, and B3, D3 for timer 2. Okay, I could have made that a little bit bigger, but if you go into the notes, you'll see that. Also, you could just look at your alternate pin sheets alternate pin functions. It'll tell you. They are referred to as OC0A. So there's no R. It's just the output compare 0A bit. Output compare 0B. Output compare 1A. Output compare 1B. Output compare 2A. Output compare 2B. Okay. So those, if you look on your pin description inside the manual, you'll see those pins. So when I say here that you've got to enable the DDR bit, it depends on which timer you're on and which channel you're on. So compare output mode. It looks like there's a little bit more. Compare output mode. Now, the waveform generator takes in a bunch of stuff. First off, it knows if an output compare match has happened. It knows what waveform generation mode you've selected, and it's got the COM bits. And it's got 2 COM bits for each channel. We've got 2 channels. Okay. So let's go into that a little bit more. Okay. Here is the waveform generator. This is what comes out. This is the actual output, a 0 or a 1. First off, we've got 2 fields, the COM field, one for channel A, one for channel B. Come back here, one for channel A, one for channel B. I just wanted to change my pen color. And if you look at how those are set, in 0, set 0, the output pin is disconnected, meaning that multiplexer is just sending port values through, not from the waveform generator. So we have no connection there. In all the rest, interesting stuff happens, specifically on a compare match. So when something happens here, something will change here. So on a change here, that will directly affect a change here. Specifically, we've got 3 options. It can toggle, it can clear, or it can set. For our purposes of making waveforms, most of the time we're going to be sitting right here, toggle. Okay, so 1 is toggle, 2 is clear, 3 is set, meaning set will just set it to 1. So if multiple events happen, it'll just stay 1. And finally, 0 is disabled. Okay, so when we set these up, we set this up on a per channel basis, channel A, channel B. Now, to go back here for just a second, what I want to call to your attention right now is this is for non-PWM modes. These bits mean something a little different when you're in a PWM mode. So for non-PWM modes, we're talking about just normal and CTC. PWM phase correct, PWM fast, those are all PWM modes. Okay. So for this, we only care about normal, toggle, clear, set. So what does this mean? If we turn these two bits on in CTC mode, for example, CTC mode we know counts up. We just saw this diagram, counts up and resets at that point. Well, if you have the COM bit set, excuse me, hold on. If you have the COM bit set, this output pin, that physical pin, is going to toggle, because if you set it to 1, toggle every time you get a reset from OCR back to 0. It'll toggle. So for homework, you had to have an interrupt and you had to set it to 1, or you had to toggle the pin bit. And that gives you a little bit more flexibility because you can toggle whatever pin you want. But if you want to have a whole lot going on at once, it is perfectly legitimate to say, all right, it has to be this output pin. Specifically, though, it's a 50% duty cycle. And that's the thing about COM mode, okay, compare output mode, waveform generation mode, in non-PWM modes. In non-PWM modes, it's always 50% duty cycle. It's 50% on, 50% off. Okay? A 25% duty cycle would be on for 25% of the time, off for 75%. This is 25% duty cycle. It's about how long it's on. Now, the thing that we can do, though, is we can change the frequency. So we can modulate the frequency based on whatever value we put into the OCR register. If we put a large value in OCR, our period is longer. And if you have a larger period, what does that mean about your frequency? It's lower. It's an inverse relationship. The larger your period, the lower your frequency. The larger your frequency, the shorter your period. Okay? Again, frequency is 1 over the period. So it's inverse proportional. Now, what is your output frequency? Here's the formula right here. Your oscillator, your output frequency, your output compare frequency is equal to your system clock divided by 2 times n, where n is your prescaler value of 1, 8, 64, 256, 1024. That's for timer 0 specifically. Okay. That's your prescaler value. And then OCR 0, whatever's in your register, plus 1. Now, why the times 2? Because you need to toggle once, twice to get a full period. You have to hit 2 of these. So your frequency is system clock over your number of ticks, which is analogous to your period. Okay? So when you want to calculate and make a square wave of a particular frequency with a 50-50 duty cycle, all you need to do is take care of your COM bits, set them to 1 for toggle, set up your clock source bits to be whatever your appropriate clock divider is, and you've got a output frequency. The third thing, which has nothing to do with the timer, again, is you have to set DDR, your data direction register, to make sure that this pin is an output. Okay? So all we've done is add in one more field, and it gives us automatic waveform generation on a particular pin. Okay? The larger your OCR value, the longer your period. And if you want a particular period or a particular frequency, you can do that. By the way, if I told you, give me something with a particular period, all you have to do is invert that formula. So you would take 2n times OCR 0 plus 1 over frequency of your system clock. Okay? So if you want a period, it's just algebra, swapping things around. Okay. So a couple of example calculations here. Assume that you have 8 megahertz for your crystal frequency, and you need a 50 duty cycle, make a frequency of 500 kilohertz. You can absolutely plug those numbers in. You want 500 kilohertz, you have 8 megahertz, solve for your OCR value. All right, now what we did here was we solved for n times our OCR value, because n is our prescaler, and there might be multiple prescaler values that make this work. So we get it down to, okay, OCR 0 plus 1 times n is equal to 8. So if n is 1, then it's just OCR plus 1 equals 8. So therefore OCR is 7. If n is 8, well, then we divide both sides by 8, and we get OCR is 0. Okay, and our prescaler is 8. So either one of these would do the same thing. Obviously, if you try to divide a 64, you'd end up with like a negative number or a fractional number, and that's not going to work. Okay, usually we want to use the lowest prescaler, because that will give us a more fine-grained control. Okay, so specifically we mentioned already that on the 328P, timer 0 is on D6 and D5, or D5 and D6. Timer 2 is a little different. It has 2 different physical pins that it outputs on. Okay, and there are a few more differences. Waveform generator in timer 2. It's the same stuff, but different pins. Okay, this is the Mega 32 version. In the 328P version, 328P version, it's B3 and D3. Slight difference. Okay. Oh, okay. I take that back. I'm mislabeling this. So this is only showing one of the comparison channels, because the 32 only has one comparison channel on timer 0 and timer 2. Does anybody remember what the huge difference between timer 0 and timer 2 is? There was one major difference. Timer 0 and timer 2 are both 8 bits. Timer 1 is the 16-bit timer. Yeah, different prescalers. They've got that one extra set. They can do 32 and 128, but they lose external counting. Okay? But other than that, about the same. It does mean, however, with that divide by 32 and divide by 128, you can have a finer control, all right, of your timing. Timer 1, timer 1, it says has 2 waveform generators. Yeah, in the 32 it does. It's the only one in the 32 that does. But in the 328P, everything has 2 channels, so it's might as well be the same. However, the timer 1 is still more advanced in the 328P for the following reasons. Unlike timer 0 and timer 2, which only have 3 bits of waveform generation, timer 1 has 4 bits of waveform generation. And it still has one more thing that we can do that is going to be interesting here. So here are the 4 bits and all the things that they can do. Specifically, let's just look at these. The ones we've talked about already, normal mode and CTC mode. Normal mode always counts up to the top value of all ones. Because it's a 16-bit timer, it counts up to FFFF, or 64K. CTC mode, yeah, it's the same thing. It counts up to whatever is in the A channel register. OCR 1A, because it's timer 1, 1A. There is another CTC mode, and this one counts up to a new register. It's just a register. It's a 16-bit register called ICR1. When we get to the end of the chapter, we'll talk about what else ICR1 is used for, but it's handy. The reason it's handy is as follows. Let's just go over a quickie example here. So here we've got time and t count 1. So t count 1 counts up all the way to, or as a maximum of FFFF. That's if you set normal mode, right? Normal mode always counts up to that. If you are in CTC mode, it counts up to OCR1A. So to start with, it's the same thing, but things get a little different here. So I put, that's the value that it's at. So it's going to stay parallel to these lines. As best as I can maintain parallelness. Okay. And we can have the OC1A bit. And every time it does this, right, every time it resets, we can have it toggle. Starts out at 1 maybe, toggles to 0, goes up to 1, toggles to 0. Those should be equally spaced. The only reason it's not completely equally spaced is because I'm bad at freehand drawing. Okay, we could also have a OCR0B channel, because we can. We have two ink color. We have two things. So OCR0B, though, if we set OCR1B to be this level, and we have an output here, OC1B, it gets a little bit different because here it's very clear that we're resetting and toggling at these points. If I start looking at the values that OC1B is going to happen, it's going to trace exactly over the red line because that's what the free running counter does. It only resets on the channel A number. But what does that mean for the output value? Well, it's going to reset every time it crosses from a low to a high. Okay, now, so it's going to reset right here. I got to do a few temporary lines here. So it's going to toggle right here. Then it's going to continue on and toggle here. Continue on, toggle here. Continue on, toggle here. So what this means for us is we are getting exactly the same frequency. If you look, every time it's the same distance. I know that those lines aren't exactly the same distance, but they should be. Looking up here, it's a little bit better to see. We're always going the same amount, same distance between those 2 points. We're just getting it shifted by a little bit. So this is not a different frequency. In fact, it can't be a different frequency, not a different frequency. It's going to be the same every time. So if we use ICR, the ICR register, then it'll be a little bit different in our PWM modes. But I just want you to understand that this is a thing that happens, right? When we're doing a waveform generation on output compare A, and we're using CTC mode, we really only get one frequency. Yeah, sure, we can get 2 different waveforms, but we're always going to get one frequency. Okay? When we get to PWM modes, this diagram gets a lot more interesting, and we'll see how that works. Okay. So, and then everything else in here, all the ones that aren't dark red, are PWM modes. There's one mode that isn't a mode at all. Mode D. Mode 13 is not any mode. but the rest of them are all PWM modes, and we'll get to those later. Okay? Specifically, later. If we are in a PWM mode, or rather, these are in non-PWM modes, it's the same thing. Toggle, clear, set, and disabled. By default, everything comes up in disabled mode. Okay, so to change your homework would not be that great a deal. Our homework was something like this. We wanted to make sure that we had an ink color that could be seen on the screen. An ink color that could be seen on the screen. There we go. We wanted to make sure that we were in CTC mode. And we wanted to make sure that we had, what was it, 7.5 microseconds between toggles. So CTC mode is a binary 1, 0, 0. We did want to use timer 1, right? Timer 1. So technically, it's 0B0100. It's 4 bits. Okay? And we need to calculate it out. And I said use a system clock frequency of 16 megahertz. All right. So I'm going to have to get a calculator out for this. All right. So to calculate out the number of ticks we need, I know that 16 megahertz okay, our crystal frequency is 16 megahertz, is the same as 62.5 nanoseconds for the period. I did 1 over 16 million is 62.5 nanoseconds. So to get our number of ticks, I'm going to take 7.5 microseconds, -6, and divide it by 62.5 nanoseconds, -9. Timer ticks are equal to exactly 120. Okay. So to start this off, we basically did a setup. We had to set up OCR1 equal to 120. Yes, this is C. I'm not dealing with high and low registers. We had to set up TCCR1B with our clock source and the upper 2 bits of our waveform generation bits. So I'm going to say that my clock source is 0B001, shifted left by CS10, and actually I should have parentheses like that, ORed with specifically the upper 2 bits. Right, the upper 2 bits are in B, the lower 2 bits are in control register A. So what do? 0B01 shifted left by WGM 1 1. 1 1 because it's 4 bits total. This is 1 0 1 1 1 2 1 3. Ooh, I did mess it up. That should be shifted over by 1 2. WGM 1 2 is this position. Next, TCCR 1A, that's just those 2 bits. 0B00, that's this part here, shifted left by WGM 1 0. And then I had an ISR. So I had to enable in TI. Hold on, erase. You're trusting somebody who's memorized half the manual and he didn't do it very well. So TI MSK1 equals T, nope, equals pen, OCR 1A. Okay, because that's what's going to trigger it. We put into OCR 1A the number 120. We put out on OCR 1A.
It's not the register.
Is it IE?
It's IE.
It's IE. OCR IE. Is it a 1A? OCR IE 1A. Yes? Okay. Sorry. Yes?
And the last part of the line where TCCR will be, what is the number that we're going to use?
1, 2. It's 1, 2 because this is the timer number, which timer we're on, and this is the bit number. So this is bit 2 of this, and we're on timer 1. So it's WGM for timer 1, bit 2. All right. And then we had an ISR somewhere down further down the line. ISR, blah, 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 OCR 1A underscore vector. That's not quite right, but you get the idea. It was timer 1 OCR A vector. We don't need this anymore. All we need to do now is add one extra piece of this, okay? And the extra piece is right here on register A. Let me just quickly, oh no, that book isn't going to have the right thing. Who was taking notes earlier or has the IO sheet? I want the COM bits. Which register are the COM bits in, B or A? They're in A? Okay, I thought they were, that's why I left some space here, but always good to check. So all I'm going to do is I'm going to add in an extra piece. I'm going to put in toggle, which is a 0B01, shifted left by COM A 10. Did I do that right, or was it COM? It's 1A1, 1A0. 1A0, okay. So it's, again, timer number, channel, bit position. Okay? Timer number, channel, bit position, TCB. All that does is it activates the waveform generation module, and provided that somewhere up here I said DDR B, and I set that to a 1 in the right place, and I forget what it is. I think it might be 3. What did I say it was earlier? Timer 1, channel A. What pin is it? I would just go back to a different slide, but it's going to erase all of this.
Oh, wait, timer 1, B1 or B2?
Is B1 or B2? What's channel A? Is it B1 or is it B2?
Channel A has...
You know, you've actually got the slides open. You could go to the slide.
It's B1.
It's B1? Okay, so that's B1. So specifically, it only is going to generate that square wave on this pin. It's the only one that it can do it on. That's a hardware limitation. If I had instead done channel 2, I could have done it on a different pin. Okay. And you saw that I would have gotten the same frequency, but it would have been shifted over by a bit. All right. So that's the only change I made right there. This line was augmented. That line was augmented. And I no longer need an interrupt on the mask register. The only thing is I can't have the toggle appear on whatever pin I want. Okay? So that's waveform generation part the first. Okay? The other thing that timer 1 can do, which makes it really good, is it can be, Your high school gym coach. Good. What? Your high school gym coach? Mr. Maxwell. All right, we'll call him Mr. Timer 1 is now Mr. Maxwell for the rest of the course. So, Mr. Maxwell in high school, did he make you run laps for like National Honor Society or whatever it is that you have to have a certain fitness level, fitness tests? You guys remember this? You were engineers. You probably weren't thrilled with this week of tests. You maybe.
Yeah, I did that.
You did that. All right. And what did they do? You had to run a mile. And y'all had a track, I assume. So you had to run like 4 times around this dumbass track.
1,600 meters, 400 meters left.
Sounds unpleasant. I'm sure you were a big fan of Mr. Maxwell. Well, so what did he do, though? He stood there. I had a guy, he was Coach Medeiros. Lovely human being. Little on the large side. He couldn't run a mile, but he made us run a mile. So he sat there, big mustache, with a stopwatch. Okay? And he sat there with this stopwatch. And every time we ran around the track, so here's the track. Oh, maybe I have to do a different color. There was my track. And he would stand right here. And I, the schlub that I was, would start walking around. Still not using the right ink color. I'd run around. And we all started at the same time. So the track kids were flying by me. They had already completed 2 laps by the time I was here. But I got around here, and he told me, it's been 8 minutes. What? I was a small kid, all right? Small kid. And it took me 8 minutes. I pulled the number out of my rear end. But he started the clock at the same time. Everybody started running at the same time, and he started his clock off at 0. When I crossed it, he just said 8 minutes. He read it off the timer. And so I keep running. And this time I was kind of annoyed. So then he told me when I crossed, he said 15 minutes. Now, does that mean it took me 15 minutes to do the second lap? No. What did it mean? It means I took 7 minutes. How did you get 7 minutes? 15 minus 8 is 7. It was up to me to remember that the first time I crossed the finish line was 8 minutes. Of course, by this time I'm so oxygen deprived, I don't even know what numbers are anymore. But we did this 2 or 3 more times until I got around the track for a mile or whatever it was. And this is what Mr. Maxwell is. Mr. Maxwell being timer 1. Mr. Maxwell.
He was actually elementary coach, not a gym teacher.
All right, well, that's just, we can't use him for the metaphor anymore. All right, if he was your elementary school coach, no, he's not Mr. Maxwell anymore. We'll call him timer 1, all right? So timer 1 has this ability to tell you when events occur, and that's super handy. For 2 basic ideas, measuring duty cycle or measuring period. What Mr. Medeiros was doing for me and what Mr. Maxwell was doing in elementary school was he was measuring your period, how long it took to get around the track, okay? If I had Mr. Medeiros standing here and then Mrs. Oh, we just called her Skeletor. We just called her Skeletor. Whatever. So if I had somebody over here telling me when I got to the halfway point, then I could tell myself how fast I was on the first half versus how fast I was on the back half. Okay? So if I had we'll call her Mrs. Medeiros. All right. If she told me it was 3 minutes here, and then I was told 8 minutes here, what does that tell me about my speed on the first half versus the speed on the second half? Yeah, I ran a quarter mile in 3 minutes, and then I ran another quarter mile in the remaining 5 minutes. Okay? So that's duty cycle for you. Okay? But also period. And here's the deal. When we had a comparator, when we were running output compare, anytime the OCR register matched the free running counter, a flag was set. Right? We had free running counter, T count, a comparator happening here. with an OCR register. It doesn't matter what channel or what timer. And then it would set a flag. Well, capture mode works almost in reverse. We have a flag, and when that flag gets twiddled, it takes whatever the value is in T count and saves it for us. This is the equivalent of Mr. Medeiros yelling 8 minutes at me, followed by show some hustle, Vile. Okay. I was traumatized, all right? I wasn't always as well adjusted as I am today. It takes that value when this occurs. So instead of setting a flag when something is equivalent, we save the value when an event occurs. So it happens in reverse order. Here's what goes on, all right? Here's our event. We have a particular pin that an event occurs on. And over here, this is my 32, not my 328P, but I can find it. Let's find, there it is, ICP. Okay. By the way, this pin, if you look at the pinout for the 328P, what you're looking for things like OCR0, OC1B, OC1A. Where's my OC2? You just look for them, and that tells you what you're put on. If you don't have my notes handy, you go to the pin configuration page. But there it is, ICP1. Ignore this for a second, okay? Ignore the mux for a second. Just assume that it goes right through this noise canceller. The noise canceller is there to prevent things like bounce and weird gross stuff from happening. And it goes into an edge detector. It detects a high edge or it detects a low edge. And then that can trigger its own interrupt or do some other stuff. But when this edge is detected is when it grabs data and saves it. You don't save it. The processor saves it. It's a hardware process. And that's all that matters. So it all happens in hardware once it's been, once it's been enabled and once it's been set up. Okay. This piece that I told you to ignore. Let's talk about it briefly. What is this device? It's got a plus and a minus, and it's a triangle. Charles, have you gotten to this yet in 202? Say again? It's an operational amplifier. It's only an op-amp configuration if you have some kind of negative feedback. If it's just two inputs, we usually call it a comparator. Okay. If one is higher than another, it goes high. Otherwise, it goes low. This is a thing, an analog thing that is built into the 328P. There are two analog pins. There they are right there, AN0, AN1. So you can have some analog comparison, or alternatively, you can compare it to the band gap reference. Let's just skip that for now. It is a source of input capture. The more common source of input capture for us is the input capture pin. Okay. So going back to timer 1, there are 2 bits that we have to deal with. Okay, this is our data chain, our data path, I should say. We have 2 bits here, depending on how we set them. Okay, we can either turn on or disable the noise canceller. It says 4 successive equally valued samples. So it's sampling in hardware, but it means that it samples at some discrete interval. And if you go low here, but then you bounce high, that's not 4 samples. So even though you've got sample high, then you've got noise, and then samples 3 and 4 are all high, that's not enough to trigger. We have to have 4 successive samples, 1, 2, 3, 4. Here we have 1, and then we reset to 0. So we have a noise canceller. Then we have, and this is sort of the more useful one, do we want to capture on rising edges or falling edges? Obviously, the analogy here is if I was running around the track backwards, Coach Medeiros would be a little bit confused. He wouldn't necessarily call out the time to me if I was running across the finish line backwards. So if we only want to look at rising edges, then I would get 1 capture here, and it would tell me 3 minutes. and then another capture here, and that would tell me 8 minutes. Actually, to keep with the analogy, I should say that this was at time 0. This was time 3 minutes. That was time 8 minutes. Really, though, we're not talking about minutes. We're talking about cycles of our timer. Okay, if you do want to use the analog comparator, you have to set another bit. Don't worry about it. Really, we just care about our edges, because 9 times out of 10, we're getting it from an external pin. So, measuring duty cycle and pulse width. That's it, okay? If you want to measure the period, there's going to be some number of timer ticks, and all you have to do is trigger on a rising edge and record the time. So this might have a number 1, 2, 3, 4. It's a 16-bit timer. And then you wait for the next input capture. And when that happens, this might be 3,000 hex. So the question is, what is the period? Let's assume that our crystal frequency, to make our math easy, is 1 megahertz. That means that our system period is 1 microsecond. So this would be, if it's an unprescaled clock, just assume for now that our prescaler is 1. What is our period in seconds, or any SI unit of seconds? How would we figure that out? Is it 3,000 hex times 1 microsecond? What?
It's just 1 microsecond. That's the period.
Nope, because that's 1 microsecond. Okay? So this is very similar to gas mileage. Let's go there for a second. Assume for a moment you don't have a trip meter. You only have your odometer. It tells you how many miles you've driven since the start of the car, right? So when you're at empty, you fill up your tank and you write down your odometer mileage. So let's assume you've got a relatively new car. You record 3,000 miles. You're at 3,000 miles. Then you wait till you're empty again and you refill your tank. And now your odometer says 3,356. What is your mileage if your tank holds 10 gallons? $35.6 miles per gallon. It's the same thing here. You just took 3,356 minus 3,000. Well, here we're going to take 3,000 and subtract 1,234, and that gives you, what's 10 minus 4? C, that's right. And this would be F minus 3. Everybody see what I did there? Yeah, it's 10 hex. So F minus 3 is ED. C, F minus 2 is D, and then 2 minus 1 is 1, so that's 1 DCC. Well, what is that in decimal? Because that's going to be a thing. We can pretty easily calculate that, because it's going to be 4,096. That's the 1 in the most significant place. Plus D is 13 times 256, because that's 16 squared, plus 12 times 16 plus 12. Put that all together, 4,096 plus 13 times 256 plus 12 times 16 plus 12 gives me 7,628. So that tells me my period, if these are my two values that I've recorded, are 7,628 microseconds, roughly 7.6 milliseconds. That's how you measure it. Yes, Sri?
Where'd you get the 49
take 16 to the third power. Okay, because we have the 16s to the 0 place, the 16 to the 1s place, 16 to the 2 place, and 16 to the 3 place. So it's 1 times 4,096 is 4,096. Okay, now what that means in terms of code, let's just assume that we're dealing with polling for a moment, is you're going to sit and, still don't have a pen that writes, you're going to poll the TI flag register 1 for the input capture flag. At that time, you're going to sit here and wait for this to occur. Once it occurs, that means that on that input pin, you've seen an edge. Okay? Assume that we've configured it for rising edge right now. What you need to do is then say time 1 equals input capture 1, the register. So I might be mixing my register names. Quickly, let me grab my I/O sheet here. I/O sheet. Ooh, I might be without an I/O sheet today. Would anyone care to lend me their I/O sheet? Yes. Okay. So the flag that I want to look for here is the TI flag register right there. ICF1. ICF1. And the register that's all going to go into for timer 1. Timer 2, timer 1. ICR1. Not ICP, ICR. Input capture register. Then I'm going to poll the TI flag register for ICF1 again. It's going to sit there doing this over and over and over again. Then I'm going to say time 2, because once that happens, we've seen another rising edge. For time 2, I'm going to again say equals ICR1. When this gets done, that means that ICR1 has a new value in it. So then to figure out my period is going to be equal to time 2 minus time 1. Okay? Everybody has a microcontroller that does this process thousands of times a minute. Okay? This kind of process is exactly what your car uses to measure the crankshaft speed. Okay? Because we know that at a certain degree past vertical, we need to fire a particular spark plug, right? We need to fire at a particular cylinder. So what we do is we have to know how long it took to make one revolution, and we base everything on the last revolution of our crankshaft. So this kind of a concept is used all the time. If you want to measure the speed of just about anything, you do something like this. You wait for an input capture event. There are things like called tachometers. You point a tachometer at something, and when a bright spot rotates past the sensor, that counts as a, oh no, counts as a rising edge. We lost it.
What was your per line that you had written there? Can you recall?
Per
It was
line?
like per equal like.
Oh, period?
That's
Period. Pen needs to come back to life here. Just period equals time 2 minus time 1. Because this one is going to be some number like maybe 1,000. This will be something like 2,000. So your period is itself 1,000. This even works if bad things happen, like we overflow. So that T count register, right, goes up to FF and resets. Okay, so let's say time 1 is here and time 2 is here. Let's just do it with 8-bit math for a second. Let's just say that this is FF. So let's say that this was at C0. That was time 1. And this happens at maybe 20. So time 2 is 20. Time 1 is C0. What happens when you do that math? What is 20 minus C0? Well, we could convert it into decimal. That would be 32, and that's minus C0, which is 12 times 16, is 192, and 32 minus 192 is negative 160. How do we then convert that back into sine 2's complement? Because everything has to be in 8 bits. So negative 160 in binary is 128. No 64. 132. No 16. No 8. No 4. No 2. No 1. That is negative 160. And I'm gonna have to throw on an extra 0 there. So that's 160. When I do the inverse of this to get 1's complement, then I add 1 to it. Okay, I add 1 to it. I get 1 0 1 1 0 0 0 0 0. So all told, that's my number. What does this come out as? Right? When I look at this, this is still going to give me, and forget about that for a second, a positive value of 60. And that's how long it took to get from C0 to FF was how much time? Well, that's about 40. And then to get from 40 back up to 20 is another 20. And so that's my 60 right there. I played a little fast and loose with my sine bit. I apologize. The numbers didn't quite work out for me. If I'd done it as a 16-bit addition, it would have been a little nicer, okay? But there you go. There's your 60. So it all works out. So it doesn't matter about the overflow. You don't have to worry about that. Let's take a short break at this juncture, and when we come back, we will deal with chapter 16, I think.